Let's now look at a balanced three-phase system. We've now talked about complex power for single-phase systems, and we've talked about what we can do with that. We can now do power factor correction. Let's now generalize this single-phase concept to what you might see more likely to happen in an industrial environment and how we generate power, and that's with three-phase power. We have three different phases. In a schematic type picture, you could think of having a source of our power, three-phase source, and we have a load that's likewise a three-phase load. And to deliver the power from the source to the load, when we have three different phases, we have the existence of three different lines and a neutral line. We have the A phase, we have a B phase, and we have a C phase, and we have a neutral line that allows for current to flow when we have an unbalanced condition. That gives us a place for the current to flow. With a balanced three-phase system, there are all sorts of combinations or interconnection structures. What we want to do is talk about one of those right now. But if we have different interconnection structures, and we'll talk about what those might be, we obviously are going to have many different system types. We can have Y connections, and we can have delta connections, and we can have Y connected sources, we can have Y connected loads. We could have delta connected sources and delta connected loads, or we could have a mix of those. We could have Y connected sources and delta connected loads, or vice versa. We could have a delta connected source and Y connected loads. Let's talk about some of those. Actually, one such piece of that three-phase system, which is the source side. And we are going to simplify things by considering that our sources are balanced. What that means is, for a three-phase system, we actually have three source voltages for the three different phases. If we have a voltage source, we have three of those. In order for those to be balanced, the magnitudes of those three sources need to be the same or equal. So we have equal magnitudes, and because we're dealing with complex power, these are going to have phases, each of these sources, and to be balanced, these phases cannot be the same. They are actually separated by 120 degrees. So the phases are each 120 degrees apart. Let's look at one such source combination, which is called a Y-connected source. And there are different phase sequences, and we will look for now at a positive phase sequence. Let's consider now a Y-connected positive phase sequence set of sources, or this positive phase sequence might be referred to as the ABC sequence. Our source are going to be connected in a Y configuration, and that Y comes from what you would think a y looks like. We're going to have a neutral. Maybe I should make my y look like a y. Here's our neutral connection. And these are now the three different sources. This might be the A phase, this might be the B phase, and this is the C phase. So this is now V sub A, this is V sub B, and this is V sub C. And we will label those a little bit more specifically. We will actually say that this is V sub A, that node, to neutral. This is V sub B to neutral. And this is V sub C to neutral. To be a set of balanced sources that are Y-connected and a positive phase sequence, let's just give each the same magnitude, and we'll call that V sub phi. And let's keep the A phase as sort of our reference phase angle and make that 0 degrees. To be a balanced phase sequence with an ABC positive phase sequence, now we want the B phase to be 120 degrees different from the A phase, and in fact this one needs to be behind the A phase by 120 degrees. Then we want the C phase to be 120 degrees behind the B phase, but in fact we like to keep our angles less than 180 in magnitude, and so minus 240 is the same because a circle is 360 degrees. This C phase now is plus 120 degrees. That's now a balanced positive phase sequence set of sources. If we now look at that in terms of a picture, we now could think of, here's the A phase, and I'm going to sort of put this maybe almost an upside down Y. But this will allow us to talk about or communicate the different combinations of expressions that we might be interested in. Let's say this is now minus plus V sub AN. This is the A phase between A and neutral. And this now is this V sub phi at an angle of 0 degrees. Suppose this is now the B phase, so that this becomes minus V sub Bn plus. Here's the B terminal. And this one was V sub phi at an angle of minus 120 degrees. This is now minus plus V sub Cn, and that's between this particular terminal C and the neutral connector N. If we needed to draw those, we would have V sub AN as a vector of length V sub phi at an angle of 0 degrees. V sub Bn would be the same length, V sub phi, but now it's 120 degrees behind V sub AN, and likewise V sub Cn is the same length, but it is 120 degrees behind V sub Bn, or as we had said before, that's relative to 0 degrees, that's an angle of plus 120 degrees, and that's V sub C in. Those are the angles, and that's if you stood at, let's say, this particular position, and these phasors were rotating in this direction, you would see the A phase first, then you would see the B phase past this point, and then you would see the C phase, and that's the positive phase sequence ABC that we are going to use. Now, in addition to these phase voltages, the voltage between terminal A and neutral, terminal B and neutral, and terminal C and neutral, we may not be able to access the neutral terminal, and we might be interested in the voltage dropped across line A and line B. We might be interested in what's the voltage between line A or terminal A and terminal B. And we could also talk about the voltage drop between terminal B and terminal C, and the voltage drop between terminal C and terminal A. Let's now compute this line voltage, and let's now find its magnitude after we find its complex value, and compare that with the phase voltage, which is the length of each of these vectors in the phase voltage configuration. To find VAB, we can now use what we already know, which is, here's a KVL equation. We can start at the neutral and go through the A phase voltage, then we can come down here, go back up through, and return to where we started. Or writing KVL now for that particular path is now minus V sub A n, paying attention to the polarity. We went into the minus terminal of V sub A n. Now, as we come down through V sub AB, we're entering the positive terminal of V sub AB. And finally, we come into the positive terminal of V sub Bn. And by KVL, those voltages need to sum to 0. If we're interested in this value for V sub AB, because we've already defined in terms of the phase voltage for a balanced set of sources, we've defined V sub AN, or the A phase voltage, in a Y configuration, and V sub Bn. Or V sub AB is now V sub AN minus V sub Bn. In terms of these phase voltage magnitudes, V sub phi, we know that this is now V sub phi at an angle of 0, or that's just now a real quantity, minus V sub phi at an angle of minus 120 degrees. We can now convert between polar and rectangular to combine these two numbers, complex numbers, and we can factor out the magnitude, that's V sub phi, and we then have 1 at 0 degrees, which is just a real value of 1. We now want to subtract, which is right here, 1 at minus 120 degrees. Convert that to rectangular form. We now have the cosine of minus 120 degrees plus j sine minus 120 degrees. We simply now have to compute those angles knowing our trigonometric relationships. This is now v sub phi is 1. Cosine of minus 120 degrees, we can think about where that puts us. That now puts us at a minus 1/2. So we have a minus 1/2 or plus 0.5. And then we have plus j 0.866. But we also have this minus sign to contend with. This particular piece gives us a minus 0.866 for the sine of minus 120. We have a minus, where we now have a plus j 0.866 for the imaginary part of this combination of numbers. Or we now have v sub phi is 1.5 plus j 0.866. Or v sub ab is now v sub phi. We can find the magnitude of 1.5 plus j 0.866. Take 1.5 squared and 0.866 squared. Take the square root of that, and that will actually end up with the square root of 3. We find the angle or the inverse tangent of 0.866 over 1.5, giving us 30 degrees. That now allows us to say that the line voltage relative to the phase voltage magnitude is a factor of the square root of 3 bigger or larger than the phase voltage. So our line voltage, if somebody now went out with a voltmeter and measured the voltage across terminal A and terminal B, that would be the square root of 3 bigger or larger than the voltage measured between terminal A and the neutral terminal. Or V sub L, if we wanted to say that that's the magnitude of V sub AB, is going to allow us to say that V sub L is the square root of 3 times the phase voltage V sub phi. This is now our line voltage magnitude, and this is our phase voltage. Once we have a set of balanced three-phase sources, we can combine that with a set of loads, and let's just look at a simple configuration. Let's say that we have a balanced three-phase set of Y-connected sources and loads. Now we could say that we have the A phase, V sub AN, which is this V sub phi at 0 degrees. Let's say that's our A phase. So we already sketched this before. We should be comfortable with this picture. There's our neutral. We now have the B phase. And we have the C phase. Giving rise to the C terminal. We can now connect that to different phase impedances at the load end, and typically the load side is capital letters. Here's our neutral connector. Let's say this is now the A phase terminal at the load, and we will in general have some impedance in our lines between source and load, but for illustration purposes, let's forget those for now. We then could have the B phase, and we could have the C phase. Likewise, we probably want this neutral conductor between the neutral terminals in the source and the load. Now that we have this YY configuration, we can think about the line currents. We have a current between the source and the load in the A phase, which we might call I sub lowercase a capital A. We could actually have, if we have an imbalanced condition, we might have current flowing in the neutral conductor, which we might then label I sub n. We could say we have the B phase current going from the lowercase b terminal to the capital B terminal. That's then the direction of current flow by that arrow. Likewise, we can have the C phase current, which is I sub lowercase c capital C, moving from the source terminal lowercase c to the load capital C terminal, or the C phase of the load terminal. That's now a YY connection where the sources are Y connected, the loads are Y connected, and we have the appropriate balanced set of source voltages, and we have balanced loads, meaning the impedances are all the same at the loads in each phase. Z sub phi is the same in the A phase, B phase, and C phase. We will pick up at that point in a subsequent session.